Yesterday, we finished the proof of the spread lemma, which was the main engine that underlined this of recent improvements on the sunflower conjecture. And today, what I want to show you is another very amazing consequence coming out of it, which is the resolution of the Kahn-Kalai conjecture by Park and Pham. So the goal for today is you're talking about the Park-Pham theorem, which was sort of solves the Kahn-Kalai conjecture. Okay. So the Kahn-Kalai conjecture was the conjecture in random graph theory and more broadly in sort of, understanding threshold phenomena. So I want to spend a bit of time sort of giving you intuition. How did they get to this conjecture, and why sort of it's a very bold conjecture, and sort of then I tell you how we can use the tools that we've developed over the last couple of days to solve this conjecture. Okay, that's the goal for today. And I'm going to basically use an example as an illustrating example. So here's going to be our writing example for today. So we're going to have G and P. So the Erdos and Rado random graph, we have n nodes. Each edge is chosen independently with probability P. And we're going to ask, what's the maximum, what we're going to try to understand is that what's called the probability that a random graph contains some structure. So this is called the critical probability. So we're going to choose some family of structures, and my example is going to be Hamiltonian cycles, just to give some very concrete example. And we're going to ask the question, what's the minimal P such that a random graph contains with high probability a Hamiltonian cycle? And we're going to see how we can use the machinery that we developed to answer such questions. Okay? So our random example is going to be this. We're going to ask what's the minimum P such that G and P contains a Hamiltonian cycle with high probability. Okay, that's going to be our running example. So let's first make some general definitions. So we can think about a random graph as basically a random set system. Right? You have all the edges, and each edge is chosen independently probability P. So we can think about it more generally in the following way. So we have some universe U, like for example, all the edges of a graph, of the complete graph. And we have F, which is going to be some family of sets. So the critical, so let's first define it. So given P in 0, 1, I'm going to denote by mu P of F the probability that if I choose W to be a P-biased set, that there exists some set in F that is contained inside W. So this is exactly the type of question we've been analyzing for the last couple of days. So we have a set system, and we're asking what's the probability that a P random set, a set where every element is chosen independently probability P, contains one of the sets in my set system, right? And I want to show you why, and we're going to find the critical probability. So the critical probability, we're going to denote it by mu C of F, C for critical, to be the minimum P such that mu P of F is at least a half. Okay. So we're going to ask what's the minimal probability such that with some constant probability, let's say a half, we contain some element of our set system. So first I want to show you how we can recast this question about Hamiltonian cycles in this language. So we can define the following set system. So again, so the Hamiltonian cycles. example. So we can define the following set system. So the set system is going to be S pi over all permutations, where S pi is going to be the following set system. Is going to be all the sets I pi I, where pi is a cycle. Sorry. This, and here pi, which is a cycle. Right, so for every permutation, we can define a set system over all edges of the complete graph. So our universe is going to be the family of all edges, So our universe is all the edges of a complete graph, and our set system is some set of graphs, in this case, all of the Hamiltonian cycles, and asking, what is the critical probability, so let's call this Ham for Hamiltonian, of this family of Hamiltonian cycles. This is exactly the question that we were asking at the beginning. What's the minimal P such that a random graph contains a Hamiltonian cycle with some, let's say, probability a half? Okay? So we can recast this question, it's a very important question in graph theory, many questions like it, into this more general language of the critical probability of some event happening, of a random set containing one of the sets in our set system. Okay? Okay, good. So how can we go about analyzing this? So first, let's see how we can get some lower bound on this P. And the first lower bound we're going to see is going to call the naive expectation lower bound, because all that you're going to do is use linearity of expectation to get some lower bound. So we're going to say if P is very low, then even an expectation, you don't expect to contain any set in your set system. So let's do that first. That's going to be our first step toward understanding this quantity, the critical probability of a set. So that's going to be, call it a naive expectation threshold. So again, we have F, which is a family of sets. We're going to define P E of F to be the value of P such that if I sum over all sets in my family over P to the S, where P to the S is the probability that the P random set contains this set S, that this is a half. Okay? So this is a continuous function going from 0 to 1 as you increase P from 0 to 1, or more than 1 even. So we're going to ask what the first P, or the exact P, where this hits a half. And we're going to call this value of P the naive expectation threshold for this set system. And why is this interesting? So this is because of the following simple claim, which is the critical probability for any set system is at least this naive expectation. I'm going to use star here, because at some point we're going to see a non-naive expectation low bound, and this is going to be just our first attempt. So how do we prove this? How do we prove that this is a lower bound for the critical probability, for the probability that a random set containing a set in a set system? So we're just going to use linearity of expectation, like the name says. So let's prove this. So let's set P to be P E star of F. So the value where you get a half. Right, and we're going to ask what's the probability if I choose W to P biased set that there exists a set in our set system contained inside W. Well, this is, you can say it's at most sum, just by union bound, sum over all S in F, the probability that S is in W, just using union bound. This is P to the S, so this is going to be the sum of S in F P to the S. And we chose P to be this exact value where we get a value of a half. So this is a half. Right? So if we chose the probability P to be this value, this naive expectation threshold, then we get that the probability we contain a set in our set system is at most a half. Might be much lower than that, but it is not more than a half. So in particular, whatever this PC of F is, must be at least P, which we set to be this naive expectations threshold. OK, so this is a good starting point. Right? We have some way of getting a lower bound on this critical probability. But the next observation is that this is sometimes very far from the truth. And we're going to ask us questions, when is this far from the truth? And we're going to see two obstacles. So the question is going to be, maybe right here. So here's the question that we're going to ask ourselves. Is the critical probability always approximately this naive expectation threshold? And the answer is going to be no, but it's going to be no for two different reasons. One reason is going to be a relatively mild reason, and the second one is going to be a much more serious obstacle. So the first obstacle is going to be isolated nodes. OK, let's take the example of the Hamiltonian cycle. For the Hamiltonian cycle example, you can do a calculation and verify that this naive expectation threshold for this family of Hamiltonian cycles is some constant over n. Right? So it's a calculation. You can do the calculation. You have to value some constant over n. Fine. But we know that if we're going to choose the graph G and P, where P is a constant over n, then with very high probability, they're going to be an isolated node. So because of coupon collectors, we cannot choose P to be 1 over n. It has to be at least log n over n. So you can think about isolated nodes or sort of coupon collector type of reasoning. So this gives us a log n gap. OK, but log n gap is not so bad. Can it always be just a log n gap? And the second answer is going to be much more serious. And we think the answer is no. We can build examples where the gap is much, much larger than log n. And that's going to point us towards what might be like a better lower bound than this naive expectation threshold. And the second example is going to be what we're going to call covers. So I'm going to explain this next. Okay? By the way, any questions so far? Everything is clear? Perfect. OK, so what are covers? So maybe I'm going to motivate it by an example. So we're going to look at the example of the following structure. We take a Hamiltonian cycle union with a clique of size 4. Okay, that's going to be our example. So let's look at this example. So we said already the F Hamiltonian is going to be all Hamiltonian cycles. I'm going to note by F of K4 to be all of the K4s, meaning it's going to be the set of the following way. So over, I don't know how we want to denote it. So ST, T is of size 4, where ST is just a family of all edges ij, where ij are in T and distinct. Right, so we have all the cliques of size 4. And you can do a calculation that the naive expectation thresholds of this family of K4 is much more than 1 over n. It's about, have it here, n to the minus 2/3. OK, fine. But now we're going to do the following twist. We're going to take the family of going to be all of the Hamiltonian cycle plus K4. Okay? So that's going to be our next example. So we take any Hamiltonian cycle, union with any K4. Okay. So what can we say about this? So So again, you can calculate this naive expectation threshold because notice it's a simple calculation. And you can verify that the naive expectation threshold for this family, let's call this family Hamiltonian plus K4. For this family of Hamiltonian cycles plus K4 actually behaves very similar to the Hamiltonian cycles. This is also about 1 over n, some constant over n. And the reason is because the Hamiltonian cycle is much, much bigger than a K4. So when you do this calculation of linearity expectation, it sort of overcomes these very few edges in the K4. On the other hand, obviously, if I have a random graph that's going to contain one of the sets here with high probability, then it must also contain a K4, right? So the critical probability for this family of Hamiltonian cycles plus K4 has to be at least the critical probability for the family of just K4s, which we said is about n to the minus, which is at least n to the minus 2/3, right? At least the naive expectation threshold for this family of K4s, right? So why do we have this big gap between this naive expectation threshold and the critical probability? So the reason is that in this family of Hamiltonian cycle plus K4, there's a small part, this K4, that really controls the behavior of whether a random graph is going to contain this structure or not. And we're going to say if a random graph is going to contain one of these structures, it must in particular contain these K4s, and they're the ones that are dominating. So now we want to modify our definition of the expectation threshold to say, I'm not just going to look on the original set system, I'm going to look on any potential barrier, any subset system that might control it. And this is what we're going to call a cover. So I'm going to define this next. By the way, all these calculations are going to be part of your problem set, just to verify these calculations. Okay. Okay. So first, let's make some definitions. So the first definition is going to be what we call a span. So we have some universe U, in the background, and given a set T, I'm going to define the span of T to be all the sets in the universe that contain T as a subset. Okay. So this is like the upset of this. You take a set, take all the sets that contain it. Okay, you have to always go up. And now we're going to define the notion of a cover. So let F and G be families of sets. G is a cover of F if F is contained inside the span of G. Or in other words, just spanning it out, for every set in F, there exists some set T in G that is a subset of S. So the name cover might be misleading. So we're covering from the bottom, not from the top. So that's again. So remember that G, the cover of F, if every set of F contains some set of G as a subset. Okay, so I know that this is a bit confusing, but this is like the common name people use here. So I'm going to stick with this naming. So now I want to argue that if a cover of a set has high critical probabilities, then the same is true for the set. So we can use covers also as ways of getting lower bounds for this sort of critical probability. So let G be a cover of F, then the critical probability of F is at least the critical probability of G. So if you can find a cover for a set system that has a high critical probability, the same is true for our set system. And what's the proof? Again, it's going to be a simple proof. So I'm going to ask, given a random p-biased set W, what's the probability that W, that there exists some set in my set system F containing W? Well, if W contains a set in my set system F, and because every set in F contains some set in G, then W must also contain a set in G. Again, if W, any set W, contains a set in the set family F, it must also contain a set in G, because every set S in F contains some set T in G. So this is going to be, at most, the probability that there exists some set T in G, T in W. And now, if we chose P to be the critical, now if we chose P to be the critical probability for G, okay, then we know that this value is a half by definition. Then we get it for this specific value, the probability that the random set W contains a set in F is at most a half. So this implies that the critical probability of F is at least this value of P, which is the critical probability of G, which is what we were trying to prove. So again, the intuition here is simple. Every set in F contains some set in G. So if a random set contains a set in F, it must also contain some set in G. Okay. So, but we already seen one way of proving a lower bound on the critical probability of a family, which was this naive expectation threshold. And so now we can apply it not just for our set system, but for all covers of our set system. And that's going to be the definition of the non-naive expectation threshold. Okay. So given a family F, its expectation threshold is what is PE of F. It's going to be the maximum over all the naive expectation thresholds for G, where G is the cover of F. Okay. So we're going to go over all possible covers of a set system. There might be many of them. It's not clear how to actually compute this. That's a different question. And we're going to, for each one of them, we're going to compute its naive expectation threshold, one by one. And I'm going to maximize over all of them. And again, because of what we've seen, again, the claim here that I'm not going to prove, just follows what we've seen, is that the critical probability of a set system is at least its expectation threshold. Okay, so now we have potentially a better lower bound. But of course, there's now a new question, which is, okay, we know how to compute this naive expectation threshold for every reasonable set system, but how do we compute this? You have to maximize over all possible set systems or conditions. Seems very complicated. So it turned out that you can use spreadness to actually prove a reasonable lower bound here. And to get some bounds. And in fact, I'm not going to show it, but you can define a relaxation of this problem, a linear programming relaxation of this problem. We replace covers with what we call fractional covers. And then if you take the dual LP, then you're going to get again threshold. You're going to get take the dual LP to the LP relaxation of that, and you're going to get spreadness. So we are not going to prove that, but if you're curious why you're going to see spreadness plays a part here, it's because it is connected to the LP relaxation of this quantity. But we're not going to prove it. We're just going to prove it's an upper bound. So here's going to be the next claim. And this claim is going to be some way of proving some upper bounds on this exact, on this expectation threshold, the non-naive one. So let F be a family which is K spread, then this expectation threshold of F is going to be at most 1 over K. Okay? So before we're going to prove it, what's the intuition here? If a set system is very random looking, then as we've seen, it's very likely that a random set is going to contain one of the sets in your set system. Because there are many events, each one very unlikely, but you know, they're more or less independent. On the other hand, if it's very concentrated on a few elements, and you happen to miss them, then you're screwed. So this is why intuitively this notion of spreadness seems to be connected, but in fact it is very, very connected. Like I said, the dual LP of spreadness is exactly the LP relaxation, or the fractional relaxation of this expectation threshold. So let's just now prove this claim. So let G be a cover of F. Right? What do we need to prove here? Remember, PE is an maximization of all possible covers of F. So for every cover, for every potential cover of F, we have to prove that its naive expectation threshold is at most 1 over K, right? So we need to prove, we need to show that if we can now compute this naive expectation threshold for G, this is going to be at most 1 over K. Right, that's our goal. So let's see, how do we prove this? So because G is a cover of F, I'm claiming if we go over all possible sets in G, and we ask what's the size of the link of F over the set of G, what is the size of all sets in F that contain T as a subset, that has to be at least the size of F. Why? Because G being a cover of F means that every set in F contains one of the sets T. So it is contained in one of these links. So we cover all the sets. On the other hand, because we're assuming that the F is K spread, we know that this is at most the sum over T in G, K to the minus T times the size of F. We have an upper bound on how fast the links grow. So now if we just cancel F, we get the sum of K minus T for T in G is at least 1. What does this tell us? It tells us if we choose P to be 1 over K, right? If we choose P now to be 1 over K, then we get the sum of all T in G of P to the T is at least 1. But we define the naive expectation threshold to be the value P where we get a half. So it has to be lower than that, right? So the naive expectation threshold for this family G has to be less than P, which is 1 over K, right? So having a spread set system allows us to get an upper bound on the naive expectation threshold, not just for the original set system, but for every potential cover of the set system. And so it sort of gives us some effective bound of this quantity PEF. Now I'll make like a side remark, which is there is a conjecture that the value you get from spreadness, this upper bound on this quantity, is always going to be equal to this quantity up to constant factors. So this is like an open problem. It's known in some special cases. It's known actually in a lot of examples, but it's not known in general. So it could be that this is a tight upper bound. We know it's tight up to a log n factor, but whether it's tight up to constant or not is still an open problem. Okay. But in practice, in all of the known examples, it is tight. Like we don't have any example where it's not tight. So if you ever want to analyze some quantity in, let's say, random graph theory or random processes, this seems to be like an effective way of getting a good upper bound on this, expectation threshold. Good. So what do we have now? We have something that we can sort of sometimes compute or approximate, or upper bound at least. And we know this is a lower bound for what we actually are trying to calculate, which is the critical probability, the probability that a random graph contains some structure. So here is where the Kahn-Kalai conjecture comes into play. So they conjecture that really these two things are very close to each other. So now we overcame the second obstacle we had, the one of covers, and the only obstacle we have is the one of isolated nodes. And we've seen that for isolated nodes, we only need to pay like a log n extra to cover it. And this is exactly what they conjectured. So finally, we can now state the Kahn-Kalai conjecture. So the Kahn-Kalai conjecture is that for every family F, not just coming from graphs, but for any family F, its critical probability, we know it's always lower bounded by this by this sort of expectation threshold. It's also upper bounded by some constant. Some constant. Its expectation threshold up to some log n, where n is a maximal size of sets in F. So actually, the original conjecture was that n was the size of the universe, which for graphs is usually the same, n or n squared, up to log factors. But really, what you see in the proof is that the relevant parameter here is not the size of the universe, but the maximal size of a set. Right? So I'll write this sort of revised conjecture, because this is what Park and Pham proved. So the theorem of Ginian, Park, and Hui-Pham is that this is true. Okay. And now I want to tell you how they proved it. And what's this time? Okay. Now before I tell you how they proved it, I want to make some comments about this theorem now, this Park-Pham theorem. So one thing that you can see here is that we have this, again, log n factor. And we know that in some cases we must have it. For example, if the family is all Hamiltonian cycles, you can do a calculation and verify that this P expectation, this expectation threshold, is 1 over n up to constants, but this critical probability is log n over n. And in fact, one of your problems in the problem set is to verify this. So sometimes we need this log n, but sometimes we know of examples where we don't need it. And it's like an open line of research. In what cases do you need it? In what cases do you not need it? Maybe in some cases you need something in between. So this is still very much open. So we don't know of examples. We don't know of a general theory behind that. OK. And the way they're going to prove it is going to be very similar to the proof that we've seen of the spread lemma. In fact, the proof I showed you is already taking their ideas into mind that I had to simplify the proof of the spread lemma. Okay. So now I want to prove this. But before proving the theorem, are there any questions about what we're trying to do? So again, our goal is to prove that for every family, we can upper bound the critical probability by this expectation threshold, which we've seen is bounded by spreadness. But we're not going to use spreadness directly in the proof. We're just going to directly connect the critical probability and its expectation threshold. Yes. Oh, yes.
So in general, do we have any better strategy for lower bounding this expectation threshold than just taking an arbitrary cover, like some smart cover?
So like I said, spreadness is equivalent to a fraction relaxation of it. And in all the examples, we know the two things are equivalent up to constants. And in fact, there is a conjecture saying that the two things are equivalent up to constants. So in practice, spreadness is a very effective way to do it. Yeah. Okay, so how are we going to prove it? So the proof is going to be basically a twist on the proof of the spread lemma that we've seen. So let me remind you of this notion of a minimal fragment that played an important part in the proof of the spread lemma, and it's also going to play an important part here. So I'm going to remind you again of the definition of a minimal fragment. Again, we've seen this yesterday, but I'll remind you. So we have F, which is some family. We have S, which is some set in the family, and V, which is some set at this point, but no, soon is going to be a random set. At this point, just some arbitrary set. We define this family of sets. Let's write like that. MFSV to be the following thing. We take all sets S prime minus V, where S prime ranges over all sets in F that are contained inside S union V. And we're going to choose this minimal fragment, MFSV, to be some minimal element. Minimal set, let's say, in this family. So again, let me just, again, I think the thing is much better to understood by picture, so let me repeat the picture from yesterday. So we have here some set V, and we're going to have some set S in our set system. And our goal will be to try to compress it as much as possible into V. So we're going to try to find a set S prime, also in the family. And we're going to take this to be the fragment, whatever is left outside V. And we'll try to minimize its size. And again, if there are several ways to do it, you choose one of them arbitrarily. Okay, so this is the same definition as we saw yesterday. Now, remember that what we did yesterday was we chose a random set V of some density, and then we only kept the minimal fragment that was smaller than some size, let's say n over 2, and we threw away the rest. And we showed that whatever we throw away doesn't contribute much. And now we're not going to throw them away. We're just going to keep the ones that are good, that shrink inside, and we're going to keep separate the ones that are bad, that didn't shrink. And we're going to analyze each one separately. So let F be a family of sets of size at most n. And we're going to define, and we're going to choose some set V also. And choose some set V that soon is going to become like a random, a p-random set. And we're going to find two new set systems, the large and the small. So F large of V is going to be all these sets. It's going to be all the minimal fragments MSV, where S is in the family, and the side of the minimal fragment is at least n over 2. And F small of V is going to be all these minimal fragments that, S is in F, and the side of the minimal fragment is at most n over 2. Okay? So we take all of the minimal fragments for sets in F, and we partition them to two families, the large ones and the small ones. And we think of the large ones sort of as bad, and the small ones as good, the ones that could compress more. And now we'll try to analyze something about how this behaves. And here's going to be sort of, again, the main, remember we had this sort of main lemma yesterday where we used spreadness to basically argue that things here are small. They don't cover many sets in F using spreadness. Now we're going to do something very similar, except we're not going to use spreadness, but we're going to weight things here exponentially based on their size. But before we do that, I want to make one comment. If I take the union of these two families, I get all of the minimal fragments. Now, all of these minimal fragments are a cover for F. That's an important observation, right? If I take all the minimal fragments of all sets in F, they form a cover for F. Because by definition, every set S in the family contains some minimal fragment. In particular, its own minimal fragment. So already you see that we're starting to construct covers here. And the way the proof is going to go is we're going to take this part to go as part of our cover, and here we're going to use induction. And we're going to gradually build the cover to our set system, and we're going to try to argue about its expectation threshold versus the critical probability for F. We're going to try to play between these two quantities. Okay. So now is going to be the main lemma, making things work. So let P be some value in 0, 1, Q be some CP, where C is some large enough constant. F is a family of sets of size at most n. And we're going to choose V to be some, actually we're going to choose to be Q-biased set. This is the same setup as yesterday, right, which is a random set. But now we're going to analyze something a bit different. Before, yesterday, we analyzed how many sets we happen to have get a large minimal fragment. Now we're going to analyze a different quantity, but a related one. We're going to analyze what's the expected value over V, sum over all the sets T in F large of V of P to the T. And we're going to prove this is at most 100 to the minus n. So this is very similar to what we did yesterday. The difference is, yesterday what we analyzed is what's the size of the links of all of these sets, right? And we showed this is very small compared to the size of F. And now we don't have spread anymore, but we just explicitly weigh each set T by P. Okay? So it's very similar. Okay. And so basically the proof here, I'm not going to give you the full proof. It's going to be exactly the same as the proof we've seen yesterday. The only difference is going to come that you remember the proof yesterday, at some point along the way in the proof. So I'll make one comment here. So you do exactly this, so it's exactly the same proof. So the proof is exactly the same as yesterday. Here's the only difference. At some point in the proof, we basically said yesterday that the side of this link is at most k to the minus t times f. Right? So we basically weighed the side of the link by k to the minus t. Here's this was using spreadness. Using spreadness assumption. Now we have no assumption, we just explicitly, so this was the weight of sort of t. And here we just explicitly weighing it by p to the t. Just say this is the weight of a set t. Otherwise, it's exactly the same proof. Same calculation, same everything. So again, one of your problems in the problem set is just to go through the proof from yesterday and verify exactly the same proof works. Nothing changes. Good. So now I want to use this. I want to use this lemma to complete the proof of the Park-Farm theorem. So again, the idea is going to be similar to what we've seen yesterday. We're going to do the thing inductively, log n steps. The only difference is now we're going to keep this large one. So let me sort of, again, write here again the definition of large and small because we need them. So let me just remind you of these definitions and then see how to get the proof to go. So just remind you of this definition. So f large of V is all these minimal fragments, SV, where S is in F, and the size of the minimal fragment is at least is more than n over 2. And the small one of V is going to be all the minimal fragments, where S is in F, and the size of the minimal fragment is at most n over 2. Again, remember, F is the family of n sets. Okay, so now what's going to be our proof? So again, let P be the expectation threshold for F. Okay? What do we want to prove? That if we sample a set that's only log n times larger, it's going to contain a set in F with high probability. Okay. So let Q be some large enough constant times P, and let T be log n, actually. And let me use set T to be log n, which will be the number of sets we're going to sample. And we're going to sample V1 up to Vt from this Q-biased distribution. Okay? And we're going to try using one by one to try to compress F and keep on the side whatever we won't able to compress. So let's set F0 to be F. And I'm going to define recursively Fi to be I'm going to take the previous set Fi minus 1, all the small parts, with respect to Vi. And then let's use Gi to denote the large ones. The one I want to compress. This will be Fi minus 1. So again, what's the idea here? We start with the set F. We take the set V1, this random set V1. We're going to move into F1 all of the minimal fragments I was able to compress to size at most n over 2. And in G1, we're going to keep the one that I wasn't able to compress. And then keep going. So let's make some observations. So one is that every set in Fi, its size is at most n over 2 to the I. So these are the minimal fragments I was able to compress. Second thing is that claim that if I take G1 union GT union the last one Ft, this is a cover of F. Again, let's see why. That's an important observation. So G1 is all the minimal fragments that covers all the sets I was able to compress in the first round. And G2 covers all the sets I was able to compress in the second round, and so on. At the very end, I have GT and Ft. So Ft is a set that is, if I was able to compress to the empty set, well, obviously the empty set covers everything. But covered to the empty set is actually good. This shows that V1 union Vt contains some set in our set system. And if not, if this is empty, then I need to use all of those to cover everything. Right? So now we have two cases. Okay. So we're going to do this two-case analysis, but before, let me just use this lemma we've seen before, just analyze this expectation threshold we get from this part. This part is going to call this G. If the set Ft is empty, G is the cover of F. Right, so we have two cases. Case one, this Ft is empty, which means I compressed everything, so G is the cover of F. Everything was bad. I never was able to get actually Ft to contain an empty set, and so I wasn't able to contain any set in the set system. And case two said that Ft is not empty, which means that if I, for example, if I use W to denote the union of these VIs, then FT being not empty means, well, all the sets in FT has size 0, so FT contains an empty set. And we've seen yesterday this implies that there exists some set S in the family F, which is contained inside a random set W. This is the event we want to happen with high probability. So really, all that we have to prove is that this event happens with probability at most a half, right? If this event happens with probability at most a half, then this event happens with probability at least a half, and we won. Okay. So let's denote this event E to be the event that says Ft is empty. And what we want to show, and our goal, will be to show that this probability of E is at most a half, right? Everybody agrees? Right. When E doesn't hold, then Ft is not empty. It contains an empty set, which means the only way we get a minimal fragment that's empty is that if I were able to compress some set completely into inside W, the unions of the VIs, right? So good. And here we're going to relate this to this sort of lemma we've seen before, and this assumption that P was this exact probability. So let me sort of erase this board. So now let's do the following calculation. What's the expected value of all this process over the sums of all sets T in G, P of T? So this is sort of related to the expectation threshold for this G, which is potentially a cover, right? If E holds, G is the cover of F. So try to understand this for this potential cover of F. Well, we got G from composing G1, G2, G3 up to GT. So it's going to be the sum from I from 1 to T of, the same thing. The sum, the expected value, over the sum of T in GI, P to the T. But this is exactly what we analyzed in our lemma. It was, again, very similar to the lemma we used in the spread lemma. The lemma told us that this is going to be at most the sum of I from 1 to the T of 100 to the minus n over 2 to the I. So again, why? Because this is, in the first step, you have set of size at most n. We're trying to compress to n over 2. And the probability that this value over G1 was 100 to the minus n. G2, we have set of size n over 2. We're trying to compress to n over 4. We get exactly the same thing, but now the parameter n changed to be n over 2, and so on. And you can do calculation and see this is at most, 0.1. Okay. So what does this tell us? Now let's ask, what is this expected value of the same thing, of the sum T in G, P to the T, conditioned on this event E happening. And let's assume towards the contradiction that, and let's assume here that, so let's assume towards the contradiction that the probability of E is at least a half, which we want to prove this is impossible. So let's make this assumption and see why we get the contradiction. Well, what is this? Well, this expectation conditions some likely event, and this is a non-negative. So that's going to be at least this expectation, which is, so this is going to be at most, sorry. This expectation, 0.1, over the probability of E, which we said is at least a half. So this is at most 0.2. Okay? So condition on this event E happening under this assumption, this expected value is pretty small, 0.2. But what is this expected value? For every G where this event holds, G is a cover of F. So if this is true, this would tell us, let me just use this here. So for every G where this event E holds, G is a cover of F. So let's choose G that minimizes this quantity that where E holds. So it means that there exists a cover G of F that satisfies that the sum T in G, P to the T, is at most 0.2. But remember, how did we choose P? We chose P to be the expectation threshold, right? So this shows that this naive expectation threshold for this G has to be more than P, right? We can increase P even more and until we get to a half. But we chose P to be the maximal one. So this is impossible. This is a contradiction, right? So let me try to summarize what happened here, because it might be a bit confusing. So really, here's like the main difference between this proof and the proof of the spread lemma. In the spread lemma, we made explicitly a pseudo-randomness assumption that the family is k-spread. And we use this to analyze this failure probability, so it's very small. Here, we didn't make this assumption. So we have like a two-case analysis. Either we succeed, and the random set contains some set in our family with high probability, and we're happy. Or otherwise, we construct a cover for our set system whose naive expectation threshold is high. Right? So this is like the main difference. We don't throw away the bad sets. We keep them on the side. And we say that if at the end we failed, then these sets we kept on the side are actually a cover for our set system, and this gives us a lower bound for the expectation threshold. Okay? So this is, I think, the main difference, the main conceptual difference. So yeah, so now it's time if you have any questions. Come in. I think it's good for you if you try to read it also on your own, because the first time that I read it, it's very simple, it's very confusing, you know. And you need to realize that we're doing these two processes at the same time. It's like a win-win case, right? Either we found the set in the random set, or we constructed the cover. And constructing the cover is now in contradiction to what we assumed about this sort of expectation threshold for the set system. So yeah. So I think this is a good time for me to stop. Yes, you have questions? Yes.
Is there some intuition for why the log n of the iterations is the same as log n?
Yes, it's for the same reason. That it's sort of you want to overcome isolated nodes. And this is true in both cases. So we've seen an example in the spread case that you did not here, but in the problem set where you need this log n factor. And here it's even more easily, just because of isolated nodes in graphs. But in both cases, it comes from the same reason. Yes?
Do you know if there's any examples between the expectation threshold and the normal threshold where you need the log n factor for a reason that's not isolated?
So sort of, I mean, depends how much you want to expand this notion of isolated nodes. Like the example we have of intersecting set systems doesn't really have a node. But there's something else that's happening of similar, there's the coupon collector thing happening. So it all seems to be happening because of coupon collector type reasons. But yeah, this is a very informal. Yeah, more questions? Good. So my plan for tomorrow is to shift gears. Tomorrow we're going to talk about an application in complexity towards proving monotone circuits lower bounds. Okay, that's it.